In the last lecture, we talked a little bit about capacitors and how to calculate capacitance. And in the following discussion section, you basically work through sort of the rules for if you combined two capacitors in various configurations. One we call parallel, shown over here. So basically, the two capacitors are hooked up, so they have the same potential difference between them. And then another configuration called series, where they're hooked up one after another. How to calculate the so-called effective capacitance of that configuration. Okay, so I want to just spend a couple minutes just recapping that because this will be something we'll be doing throughout the course when we get to circuits. So we'll talk about parallel and series combinations of capacitors and also resistors. So basically what we're talking about here is imagine we have two terminals A and B, and I've connected two capacitors C1 and C2 in such a way that basically they have the same voltage difference between them, or as we say, the same voltage drop. Okay, and so what we can do is, in effect, replace. Imagine these capacitors were in a box. We could replace C1 and C2 by a single capacitor of some effective capacitance, and if we never looked inside the box, we would not be able to know whether or not we had sort of a combination of C1 and C2 or just a single capacitor C effective. And the same goes for a series combination. If we had these two capacitors hooked up one after the other, we could replace that with a different capacitor C effective. So the effective capacitance of two capacitors hooked up in series versus parallel would be different. But we could still replace, the two capacitors inside this box by another single capacitor, and we would never be able to tell the difference between two of these capacitors hooked up in series versus a single capacitor there that would replace the pair. Okay, so this is what's called an effective capacitance, meaning that we can basically think of these two as being a single capacitor. And in your co-op exercise, you basically worked out what the rules were. I'm just going to just very briefly recap that. So imagine we put, there's a voltage difference between A and B. So across this first capacitor here, let's imagine that VB was 0. I can set it to whatever I want. So I'll just say that VA was some positive voltage plus V relative to VB. So then I can calculate then the amount of charge on this capacitor because I know basically the voltage across it, and I know its capacitance, right? So I know that, for instance, Q1, the charge on capacitor 1 is just C1 times V. I can do the same sort of thing for C2. The top plate of the capacitor is also at plus V relative to the bottom plate, because they're hooked up by one wire, which means these two top plates are the same potential, these two bottom plates are at the same potential. So Q2 is just C2 times V. It's the same V again, because like I said, these two plates are connected by a wire and these two plates are connected by a wire. So then we can think of then the total capacitance of the pair of these two capacitors as being just Q effective, or Q total, is just the sum of the two then, right? Because there's some charge Q1 on this plate, there's some charge Q2 on this plate, and there's a minus Q1 here, and a minus Q2 there. And I can just take this here, and I have basically a V that I can factor out, and a C1 plus C2. So then I can basically define then my C effective as this quantity here, right? So if I place a voltage across this pair of plates in this configuration, the total charge that's accumulated, which is the sum of the charges on both plates, is basically just the voltage times the C effective. So basically, C effective is just C1 plus C2 for capacitors in parallel. If I had any number, let's say if I had 3 or 4 different capacitors all in parallel with one another, in general it would be just C effective would just be the sum. This is in parallel. Another way to think about the capacitors in parallel that I think is kind of helpful, that I like to think about, is imagine, we had these two capacitors. So imagine it was just you had one giant plate, pair of plates like this, okay? And then what I was going to do to make my two capacitors that I have up here in parallel, I'm basically going to just saw off the end of this plate, and I'm going to saw off the end of that plate, okay? So they're sort of matching pairs. But I'll leave just a tiny little, bit that's connected. And then I can sort of stretch them apart. And so I can think of this as sort of being C1, and this is being C2. This is sort of one capacitor. This is another capacitor. I could, I'm not able to animate this drawing, but you could imagine if I could take them and I could stretch them apart. So this part in the middle was like bubble gums. There'd be like a long wire connecting these two. But, it doesn't really matter whether I've stretched it or not. Basically, you can think of it as one big plate, which is just the combination of these two, and then C effective is just the sum of the two. Because as we know, for parallel plate capacitors, the capacitance is just proportional to the area, right? And so if I merge these two plates together, or almost merge them, it's just the sum of the two areas. So that's kind of, I think, a handy way to think about how to combine capacitors in parallel. So when you add up two capacitors in parallel, you're basically, the effective capacitance is just the sum of the two, all right? So another way to add them up is in series, as I've shown here. So again, let's imagine the bottom voltage VB, we'll call that V0. We'll call this some positive voltage. V sub A is, we'll say it's a voltage V larger than VB. All right. And then so we're going to apply this voltage across this pair, and then we can see what happens, right? Well, so this middle section, so this bottom plate, is a piece of metal that's connected by a wire to this top plate. So this entire sort of eye-looking section here in the middle is one piece of metal that's sitting at one potential. Okay, I'll call this, just for argument's sake, I'll call this VC. Okay, that's the voltage of this whole I-beam here. Okay, or this eye-shaped piece that I've drawn. So then so in that case then VA minus VB is going to be equal to V. And that's going to be equal to basically the voltage from here to there plus the voltage from here to here, right? So basically the voltage from here all the way to the top is just the voltage between this bottom plate and this top plate, and then this, which merges into this bottom plate to this top plate here again. So that's just VA minus VC minus, or plus, VC minus VB, right? So you can see there's a minus VC here and a plus VC there, so those cancel out. All right, so this voltage here, so you may be thinking, well, why did I write this in such a funny way? So this voltage here, VA minus VC, is just the voltage across this capacitor, right? So that's just, so imagine if there was some charge amount on here, Q1, and some charge on here, Q2. Since this is the voltage across the capacitor, this is the same thing, our definition of capacitance is basically just Q over, or capacitance is Q is equal to CV, so V is just Q over C. And likewise here, this would just be, this is the voltage across this capacitor here. Ooh, I mixed this up. Sorry, that was the top capacitor. The top capacitor was Q1, not Q2. So VA minus VC was Q1. My bad. Q1 over C1. VC minus VB is Q2 over C2. Sorry, mixed the bottom and the top. So if we think a little bit, we can actually figure out what the relationship between Q1 and Q2 is, right? So for instance, if I've charged this up to some potential here, let's imagine I'm piling up some positive charge plus Q on this plate, on this top plate, okay? And so in capacitors, we know that basically the charge on the top plate should be the same as the charge on the bottom plate. So this bottom plate should then have a corresponding charge minus Q. We've called that Q1, but I'm just going to call it Q for now. Now, here's the thing. This piece of metal in the middle, right, like I said, this was one big, this is the bottom plate of this capacitor and the top plate of that capacitor connected with a wire. This was all one piece of metal. And so initially, before I put a charge on here, this was neutral. There was no net charge on this. And it's going to remain neutral. There's no way of actually putting charge on here. It's not actually physically touching in these plates. So if there's a negative charge on this on this plate up here, there must be then an equal and opposite. So in this case, that was negative. This must be a positive charge, Q, of exactly the same magnitude on this bottom part of the middle section here, right? Because basically, if this whole thing wants to be neutral, there must be as much negative as positive. So this should have an equal amount of charge, but in the opposite sign. So this would be minus Q here, plus Q there. And then likewise, if there's a plus Q on this plate, and then the bottom plate should also have a minus Q. Okay, so we've just shown, sort of just by charge conservation, that the charge on each one of these plates is Q. Okay, so actually we found that Q1 and Q2 are the same. So we'll just call it Q. There's no point for the subscripts. So then we have this relation that V, right, across the pair of capacitors is just Q over C1 plus Q over C2. I can factor the Q out. So it's basically Q 1 over C1 plus 1 over C2. Our original definition of capacitance was Q is equal to CV, or in other words, V is equal to Q over C. So we have a V here on this side, we have a Q here on this side, and we have a 1 over C1 plus 1 over C2, right? So in other words, what we've shown in writing here is that our C effective, or our 1 over C effective, is equal to 1 over C1 plus 1 over C2, right? So in series, my mistake, 1 over C effective for a pair of capacitors is 1 over C1 plus 1 over C2. In general, it would basically be 1 over C effective would just be the sum. If you had, instead of 2, you had 3 or 4 capacitors all chained up, it would just be 1 over Ci summed up. Okay? So that's basically what we have, are how to add capacitors in parallel and series. And then you can imagine more fancy combinations. So you could, for instance here, you could put 2 capacitors here in series in parallel with this capacitor here, and then another capacitor here in series. And you can basically reduce this one. If there were 2 here, you could reduce that to use the series rule to reduce that to an effective capacitance, use the parallel rule, and sort of just keep iterating to get an effective capacitance. So from what we've shown here, one way to, for instance, increase the capacitance of a capacitor is you could add up a whole bunch of capacitors in parallel. But, are there other ways of increasing the capacitance? Let's say, if you have these 2 parallel plates, is there another way of making the capacitance larger? And the answer is yes. We can use something called a dielectric, okay? So if you remember the capacitance for a parallel plate capacitor, right? Basically the formula goes as C, goes as the area between the plates divided by the distance between the plates times epsilon naught. All right, and that's basically what the capacitance looks like for a parallel plate capacitor. So if you wanted to make the capacitance larger, you could make the area larger or the gap smaller. But at a certain point, that doesn't become feasible anymore, right? I mean, you could just make things bigger and bigger and bigger, but then at some certain point, you want to be able to, be able to stick it in your pocket. So what a dielectric effectively does is to increase this epsilon naught value, or it's basically, epsilon naught is a value for what's called the permittivity of free space. And so what we're doing then, or what we're going to do, is if we insert in between the capacitor, instead of having, just empty space, if I insert a material that we call a dielectric, we can actually effectively enhance this epsilon naught value. So we can increase the capacitance of a parallel plate capacitor without having to increase its dimension, like either narrow the gap or increase its lateral dimensions. All right? So how does this work? Well, okay, let's imagine we have some electric field. So I'm going to just draw pointing down. All right. You could imagine this is in between the plates of a parallel plate capacitor. And so let's imagine we have a dipole in there. Okay, so we talked a lot about dipoles earlier on in the class. So let's imagine we have a dipole. So there's a dipole is basically a plus charge and a minus charge. And let's imagine this is a molecule, let's imagine, of sorts. So basically, due to the molecular bonding, you can just imagine it as being sort of approximated by a little rod. The stick is basically the molecular bond that holds those two nuclei together. All right. And so in one of your problem sets, you calculated, okay, well, there's no net force on this dipole, but there is a net torque, right? And so what will happen is that if I put this dipole in this orientation, the plus side will feel some, if you imagine, let's say, some torque about the center, it'll want to rotate like this. The plus side will want to come down. The minus side will want to rotate up like that, okay? And so what will happen in equilibrium then is that if I put this dipole in an electric field, the positive end will want to stick down, and the negative end will want to stick up. All right? So this is any kind of dipole. And so let's imagine we have a material now that's made out of dipoles. Right? So this is a single dipole. In electric field. And let's imagine we have a whole chunk of material that's made out of dipoles, okay? And actually, that's not a bad approximation. So if you remember in one of our first lectures, I picked up a whole bunch of like polystyrene, packing foam peanuts, right? That's an insulator, and those material, if you look inside, the molecules in there are basically kind of like dipoles, okay? So we have some electric field pointing down. So this material is not a conductor, so we'll use green. So let's imagine we have some kind of slab of material made out of dipoles that we're going to stick in this field. Okay? And so what will happen? Well, basically exactly what I've drawn here will happen, except on mass. So you can imagine here's a dipole, here's a molecule. The minus side will be pointing up towards the top. The bottom will be pointing down. I'll have lots of them lined up head to tail, basically, right? They'll all be pointing up, with a negative up and the plus down. So it looks something like this, and it'll be all over the material, right? This is just one chain of dipoles. So in the middle part, and this isn't the best drawing, but so if I'm going to blow this up. So at the top, I have a minus and a plus, right? And then the next one down, I'll have a minus and a plus, and then a minus and a plus. So basically the minus and the plus here are very close together. So there's basically no net, there's no net effect from having these guys here. These basically cancel out. All these pairs cancel out. So what you can think of then is you're just left with this little one negative charge is left on top here. So what you'll get is basically a net amount of negative charge that's sitting on the top surface, and a little bit of plus charge, a corresponding similar magnitude but opposite sign, on the bottom surface. And that's actually how we argued, when we were using one of these charged rods to pick up a packing peanut. We said, okay, well, there's actually some this is called the polarization charge, okay, or an induced dipole. So this material normally doesn't have a net dipole moment. When I stick it in a field, the molecules align like this, sort of up and down. And so if I have a whole slew of these molecules arranged in a solid, what will happen is I'll get some net amount of negative that accumulates on the top, some net amount of positive that accumulates on the bottom. All right, so what will happen when I do this? Well, if you just think of these things now as being kind of like a, just infinitely charged plate. So now I had this big slab material, but I said, well, nothing really exciting is going on inside the bulk because all the pluses and minuses are jammed up next to each other, so there's no net effect. The only thing that matters is this top surface where there's a little more negative and this bottom surface where there's a little more positive. So these act more or less like infinite sheets of charge, right, which we've dealt with in Gauss's law. And as we've learned from, let's say, a pair of sheets of charge, there is some net field in between them, but there is no field outside, right? So just for the time being, neglecting the red field here, if I just look at, okay, I have some plus charges here and some negative charges here, these guys will then generate some electric field, right, in this direction. So you can see inside the dielectric, there's a counteracting field. I'll call it a slab. There is an opposite field which is induced by the polarization charge on the surfaces. All right, so let me just go run through that one more time to see if you understand the logic, okay? So I have an external field that I've generated somehow, okay? It could just be between the, plates of two capacitors, okay? If I have a molecule in there that has a dipole moment, it will want to rotate, and because it'll have a net torque on it. So the equilibrium position will be such that the negative will be pointing up and the positive will be pointing down if it's a downward applied field, okay? So now if I imagine a whole chunk of material that's made up of these little dipoles, then I can kind of think of them like this, in one column, they're lined up like this. The pluses, of this one it's going to be, very close to the negative of the next one. So here basically there's no net effect because these are kind of canceling out. But at the very, very top, there is no plus on top of it, right? This is the last molecule at the surface, so there'll be some net negative that builds up, and this will happen all the way across the surface. Likewise, for the very bottommost molecule, there'll be a positive pointing down and nothing to counterbalance that, so there'll be a net amount of positive on the bottom, okay? So due to all these molecules lining up, then I have effectively a sheet of negative charge at the top of the slab and a sheet of positive charge at the bottom of the slab. And from what we've learned about in Gauss's law, when we have sheets of charge, that will generate some electric field. In this case, that would be pointing up. So that will be pointing in the opposite direction to the original applied electric field. All right. So then inside the dielectric, right, the electric field will be weakened. So usually what will happen is that this will not perfectly counteract the external field. There'll still be some net field. Okay, so for instance, if the applied field, this was E applied, and let's say the strength of the electric field was half that, the strength of the electric field that was generated by the dielectric. So we'll call this E induced, right? So then the net field then would be, this plus that, so it would be something like that. Okay, so this would be E net. So in general, what we say is that, and it depends completely on the properties of the dielectric, that basically the E net is going to be equal to the E applied, or oftentimes you just call this E naught, divided by some factor K, okay, or kappa. And K is basically telling you, it has to do with the properties of the molecules in here. So it's very material dependent. Actually, that depends on the material. It depends on the temperature of the material. Depends on a lot of different factors. It's very complicated in the sense of it depends a lot on the microscopic arrangements of the atoms. And so, we're not going to get into that in this class, but basically all that information can be basically encapsulated by this K. And that basically tells you how effectively does the dielectric material generate an electric field which counteracts the applied field. Okay, so if K was 1, then E net is E applied, which means that basically there was no net field, no induced field. So this is what happens if you have basically, empty space between the capacitor plates, or air. Air, it's not quite 1, it's very, very close to 1 though, okay? Air has molecules in it, but not that many, so certainly not as many as, a solid chunk of material. So, for an empty gap, air, or empty space, K would be 1, okay? For water, for instance, K is on the order of about 100. Okay, and so for many common dielectrics that we would actually stick in between our capacitor plates, so these are sort of common dielectrics, and I'll list a couple. So for instance, water is about 80. Glass, depending on the kind of glass, is sort of on the order of about 10. For instance, there's a particular material called strontium titanate, which actually I work on in my own research, and that can have a dielectric constant of, close to 1 million. But, for glycerin, that's something like, 40. So a lot of the common dielectrics that you would actually stick in between your capacitor have dielectric constants sort of in the range of 10 to 100, all right? And again, that's highly dependent on the properties, on the microscopic properties of the crystal structure of the stuff that you're sticking in there. I've just drawn here again a side view of a parallel plate capacitor. All right, there's a plus Q on the top plate, minus Q on the bottom plate, and I've slid in a slab of material that has a dielectric constant kappa. Okay, and so there's an electric field, right? And I'm just gonna imagine I haven't quite shoved it in all the way. So there's a little bit of the plate here which has the original voltage, but then in between here, because they're the dielectric constant kappa, let's just say it's on the order of 10. The electric field inside this material will be reduced by about a factor of 10, right? So the electric field in here will be weaker. I'm going to draw these smaller arrows just to signify that, okay? Right, and again, the reason for that is because when I stick this dielectric material in there, there's some surface charge, a negative surface charge that accumulates on the top plate due to these dipoles aligning themselves, and then some positive charge that accumulates on the bottom plate. That generates its own electric field, which partially counteracts the external field, and so then the net field is some smaller amount, okay? And it's reduced by this factor K, or kappa. All right, so we have a smaller electric field inside. So, if originally the electric field, if there was no dielectric as shown here, would be basically, V naught over D, then the electric field inside would be basically, E net is basically E naught over K. That's our definition of the dielectric constant, right? Which is V naught over K times D, because this is what our E naught was if there was no, and this is the familiar result if there's no dielectric in there. All right, so we can then figure out, what the new capacitance of this object is that has the dielectric in there. So our definition of capacitance is C is just basically Q over V, right? So we have some Q, which is plus Q on this top plate, minus Q on the bottom plate. And then what I can do is that for V, I can integrate what the electric field is inside from here to there, right? So basically if I do that, this V will be minus, let's say from A to B, E dot dl. But E in this case is V, or V naught, over K, right? And then, V naught over K times D. That's what we had over here. And then when we integrate that over this whole length, the whole separation between the plates, which we're saying is D, so the D's cancel. So our total V voltage in between these two plates would actually be V naught over K. All right. So you can see if there was no dielectric in between the plates, then Q would just be, C would just be Q over V, or Q over V naught. With the dielectric, we have the result we just obtained, which is C is Q V naught over kappa. So basically C is, that K comes on top then. So it's K Q over V naught, right? So in other words, this was, I'll call it C naught with no dielectric. So it's K C naught, okay? So what that means is that if I stick some dielectric material in here that has some dielectric constant kappa, it enhances the overall capacitance of that object by a factor kappa, okay? So if I was going to shove glass in between these two plates and glass had a kappa of 10, then if the original capacitance of these plates was, let's say, the units of capacitance is typically in farads, and I'll write that down in a second. Let's say it was, 1 microfarad. Then if I put a piece of glass in between, then the new capacitance would be like 10 microfarads. So it would be 10 times the original amount. Okay, so again, if I have some capacitor that has some, normally would have some capacitance C naught, if there was nothing in between the two conductors, then if I shove a material, dielectric material that has a dielectric constant kappa or K, as I, this is the name, dielectric constant, then the new capacitance is just enhanced by a factor kappa. So if I shove air in there, air basically just has dielectric constant of 1, so there's really no difference. But if I shove in, water, then my capacitance is now 80 times bigger, all right? And this dielectric constant kappa, again, depends entirely on the material properties than the microscopic atomic structure of the material that we're interested in. So again, if we revisit our expression for the energy stored in a capacitor, we'll call that U, right? We wrote that as 1/2 CV squared. So again, if we now have a capacitor and we've shoved a dielectric in there, then our new C would just be C naught times K. Actually, let me just write that the other way around. So K C naught V squared, right? So it's actually going to be a factor K times 1/2 C naught V squared. This would be our original energy stored with no dielectric. So basically, again, much like the amount of charge, the amount of, or the capacitance increases by a factor K by putting that dielectric in there. If you take a capacitor, you apply a voltage across it, you get some energy stored in there, U naught. Now, if you take the same capacitor, you put a dielectric in there, then the energy stored in there will be increased by a factor kappa, okay? So as it turns out, right, it's very handy to have these dielectrics because you can, by sticking this material inside, it makes the capacitor easier to manufacture because you have these two plates that are separated by, air. Mechanically, you can imagine that's not very stable, right? They may want to bend and touch each other. So if you stick some rigid material in there, A, that prevents the plates from touching, but B, that also increases the effective capacitance. So you don't have to make that capacitor much larger, or you don't bring the plates too much closer together, which can be very difficult to manufacture. You just put this dielectric in, and that solves a lot of your problems. We'll talk a little more about that in lecture. The very last thing I just want to mention is the units of capacitance, which I probably should have mentioned a little earlier, but it's not too late now. So the units of capacitance is basically, in the units we're using, SI units, it's basically units of farads, okay? And so, or F. And so that corresponds to basically, as you remember, so Q is equal to CV. So Q has units of coulombs. V has units of volts. So basically, 1 farad basically then has the units of coulombs. Coulombs per volt. Okay, but if we're asking you a question, usually you just give your answer in terms of farads. And the typical values of farads that we deal with, for a typical capacitor. So if you pick a capacitor up and you look at, how many farads it has, generally, it's a fairly small amount. Okay, so a typical capacitor is sort of in the nano to microfarad. Some of them are millifarads, but typical capacitor values are typically sort of, microfarads are sort of a very common value. And you can think of that as being the following, right? So a typical voltage you would apply across a capacitor is something like 10 to 100 volts, okay? And we know that coulombs, 1 coulomb is just an enormous amount of charge, right? Just a huge honking amount of charge. So, we typically don't deal with coulombs of charge. We typically deal with like microcoulombs of charge. And already that's a pretty big amount. So because a farad or the capacitor is basically the proportionality between the voltage you apply and how much charge is accumulated on the plates. If you applied 1 volt and you got like 1 coulomb out, that's just a ridiculous amount of charge. So typically, you apply 10 volts to something and you get, a microcoulomb or 10 microcoulombs out. So this value of C has to be fairly small. So it's typically small because we deal with small amounts of charge. Typically, microcoulombs to nanocoulombs is sort of the amounts of charge that we would deal with on a day-to-day basis. So, typical capacitor values are sort of in the micro to nanofarad regime. Okay. Sometimes you encounter some really big capacitors. So, for power applications, you get capacitors that are like in the farad regime, and that's all well and good, but they're pretty scary. You don't want to work with those too often because, if they blow up, you don't want to be around when that happens. All right, so that's it for today.